Hello deep learners, welcome to this 6th lecture of PyTorch Zero to Hero playlist, where we are going to learn about how we can build a MLP classifier which can detect handwritten digits. So let's say that you give it a digit of 1, like an image of 1, it can easily detect that it is 1. If you give it an image of 5, it can easily detect that it is 5, right? So we are going to build it from scratch in PyTorch. So take a pen and paper, grab a hot cup of coffee, and let's get started. Alright guys, so before starting, let's see how we can use GPU in our entire workflow. So till now we saw how to use CPU, but now let's see how we can move to GPU for faster computation, right? So this is how it's done. So what are the advantages of this GPU training? So first is that using GPU, we can train our model on larger datasets. So let's say that we have like lots of hundreds of GBs of dataset. We can easily train our model on those larger datasets because using GPU we do parallel computation, right? And due to that, our training and our inference speeds up a lot. Next is that using GPU we can build bigger models. So this includes building LLMs, transformers, and much larger and deeper neural networks. And number 3, as I told earlier, that GPU, it speeds up our entire training and inference because it does parallel computation. Alright, now let's see the steps of using GPU. So first is that whenever we are writing our code, we have to first start by checking that if GPU is available. So we check that is GPU available so that we can use it. So for that we use this torch.CUDA module, and how it's done is like this. So device is equals to torch.device CUDA if torch.CUDA is available. So this is a boolean which returns either true or false, and if it is true, like if CUDA is available, then we return this CUDA. Right, so if GPU is available, then this device variable becomes torch.device of CUDA. Otherwise, it becomes torch.device of CPU. Right, it's a simple like ternary operator thing. Next, we build our model. So while building our model, we simply move our model to this device so that all the computations for this model, they happen on our GPU or like on whatever device that we are in. So this is the step where we are building our model. Like this is very simple. So this is our class that we built earlier using this init module, and then we move this model to the device, right? Next, when we are defining our data loaders, there is a parameter which is pin memory, and this accepts again a boolean, right? So we set this pin memory as true in this data loader definition, so that basically it speeds up the data transfer using GPU. And also we have another parameter in this data loader which is num workers. So as you can see, this num workers, it determines how many codes or how many code processors we want to use for this entire data batching, data processing, data loading and data handling things, right? And the same thing we do both for our train and our test data loaders. And this is how it's done. So this is where we are defining our data loader. So here we mention our training data set. Here we mention the batch size. Shuffle is equals true, so that we are using a random sampler for shuffling our data. And we do our pin memory as true if we have our GPU. Otherwise, we make it false if we are on CPU. And then we specify the num of workers, which defines how many code processors we want to use for parallelly handling this data thing. And lastly, in the training loop, where we are running the loop for our batches, what we do is we move these batches of features and label to this device. And why do we do this? Simply so that all the computations related to this device or to this batches of features and labels, they happen on the same device that our model is on. So you remember this step 2. Here we move our model to this device. Similarly, we do the same thing with our data batches so that all the computations they happen on the same model. And the same thing we do in the evaluation loop also with the test batches of features and labels. Right, so this is how it's done. So here we run our loop for the batch features and batch labels in this train data loader, and we move our this batch features and batch labels to the device. Right, again it's very simple and it's done in this same process as of this one model, and like this entire process is very simple and there is nothing much complex about it. Alright, now let's talk about how we are building this handwritten digit recognition system. So first, let's see what is this MNIST. So firstly, this MNIST is nothing but it is a data set. Alright, so it is a data set on which we train and evaluate our model. Right, so this data set, it contains simply the handwritten digits from 0 to 9 and they look like this. So this is the digit 5, 0, 4, 1, 9, 2, 1, 3, 1. So like this MNIST dataset, it contains all these images and each one of them is of the size 28 cross 28. So width and height are 28 pixels. Alright, and in this MNIST dataset there are a total of 70,000 images. So it is again a very large dataset, and as I told, the image size is 28 cross 28 pixels and they are in grayscale. So you can see they are black and white. They are not RGB images, they are simply grayscale images, which means that they have just one color channel. So here there is only one color channel, whereas in RGB we have three color channels. So yeah, color channels is 1 and the number of flashes is 10, which is simply this 0 to 9. And each image, as you can see, is of 28 cross 28. Therefore you can say that each image is a matrix, right? So a matrix is like this format. So it is a tensor which represents a matrix, and there are 28 columns and 28 rows. So its shape is 28 cross 28, and what we do is, before training and building and like doing anything, we flatten this matrix into a single one-dimensional tensor. Right, so this was a matrix which was 28 cross 28. We flatten it into 28 times 28, which is nothing but 784. So now this becomes a one-dimensional tensor. So this is one-dimensional tensor of shape 788, right? And these 788 are nothing but their features. Meaning that this 788, they are nothing but our input. Right? Our input, or you can say the features. Or you can also say the number of columns that we have. Alright, so these are our feature. And what is the label? So as you guys know, for doing anything in neural networks, we want two things. One is the features, which is also known as X, which is also known as the input. And the another thing is the label. So this is our label, which is the Y, or which is the output. So how it works is, we feed these features into our model, and our model tries to generate this output or this Y. It's very simple, right? And in this case, our label or our Y or our output is a single integer which represents the number itself. So let's say that we have this 5 image. So this X or the feature or the input, you can say, is nothing but a one-dimensional tensor. So this input is a one-dimensional tensor where there are 784 features, meaning that its shape is 784. So there are many columns over here and the number of columns is 784. And our y or our output or the label is nothing but this single integer which represents the digit. So it is nothing but 5. So we feed this x into our neural network, and this x is this 784 columns of a one-dimensional vector, and this neural network, it tries to predict this y, which in our case is 5 over here. And that we do with all these images. So if we have 70,000 images, we simply do this thing with 70,000 images, right? And that is how this entire neural network training is done. Alright, now let's start building this recognition system. Alright guys, so now let's actually start building this recognition system. So first go to Google Colab and create a simple notebook. Alright, and this is the first step where we import our packages so that we can use this in our entire workflow. So here in this step, we import our NumPy, Pandas, Matplotlib. So these three you generally use for any neural network training and any neural network project, because see, first we download our dataset in CSV format. So to load that data from that CSV format, we have to use this Pandas. Next, we can't work with this Pandas data frame, so we convert this into NumPy arrays. So that's why we need this NumPy. And lastly, we use this Matplotlib to understand much better about the dataset. So we are going to see how it's done. And next we are going to import this torch, which is the code PyTorch package, which provides the CODA module, the tensors and everything. And then we need this NN module, which we use for building our neural networks. And then from this data, we import dataset and data loaders, because we saw in the previous lecture that these things make our life much easier when it comes to data handling, data processing, data batching and everything. And lastly, we import this Optim module for using optimization algorithms like Adam, Adagrad, RMS prop, momentum, energy, anything. And then we import this train test split, because let's say that we have the features and the labels. Now we want to split the data into training and test set. So we use this training set when we are training our model, and we use this test set when we are evaluating the model. Alright, so let's go. So this is the first step. So we need first the NumPy. Obviously we need the Pandas for loading the data which is in our CSV format. So import Pandas as PD. Then we are going to need Matplotlib. So import matplotlib.pyplot as PLT. Then these are the core 3 packages. Next, for working with PyTorch, we need the torch. Then we are going to use the NN and Optim module from PyTorch. So for it, we use import torch.nn as NN and import torch.optim as Optim. Then for working with datasets in PyTorch, we simply import dataset and data loaders. So from torch.utils.data, we import the dataset and the data loader. Alright, and lastly we need the train test split. So from scikit-learn dot model selection, we import our train test split so that we can split our dataset. So from scikit-learn, we import the train test split, and it is going to run. And then what we do is, once this has been done, next we are going to create this device variable. So as you remember, I told earlier that for using this GPU, we first create this device variable, right? So let's create this device variable. So device is equals to torch.device of CUDA if torch.CUDA is available. So if the torch CUDA is available, or if GPU is available, this becomes torch.device of CUDA. Otherwise it becomes torch.device of CPU, else CPU. And I also want to print it, so device. So as you can see, I am not using a GPU currently, so that is why it is saying that my device type is CPU. Alright, so this was the first step. Next, the second step is to download our dataset. So here we have to download this dataset. Then we bring this downloaded CSV into this working directory, and we use pandas to load this data. Okay, so for downloading the dataset, go to Kaggle and use this dataset. So we are going to use this one, and here we see this MNIST train.csv where there are 60,000 rows. So we simply download this, and once it has been downloaded, you go to this files and we just upload it. Alright, so it is being uploaded, and yeah, it's being done. And once it has been downloaded and uploaded into your Google Colab, next what we do is we make a pandas data frame. So as I told that our data is in the CSV format, so for loading this we use the pandas data frame. So this is how it's done. And then we do some EDA, which means we do something so that we can understand much better about the dataset. So here we are working with the dataset thing. So first we are loading the dataset. So data is pd.dataframe, and you just go to here and you just click on copy path and you just paste it. So it's loading, so let me wait. Alright, so the file has been uploaded. So we do this. Oh sorry, it is pd.read CSV because we are loading the CSV file. So it will be this CSV read CSV, and our data will get loaded. Yeah. Next we do some EDA. So for EDA, let's see the first 5 rows of this data frame. So it's simply this data.head, and this returns the first 5 rows of this entire CSV file. So you can see that there are 5 rows. So this is how it looks, and there are 785 columns. So as you know that 28 cross 28 is 784, but there is another column which represents this label, simply the number or the integer which represents what this image is. So this label is 5, so definitely this image represents 5, right? So it is that logic. And let's see the data.shape. So you can see that there are 60,000 rows or 60,000 of this data entries or samples, and each of them they have a shape of 785 columns, where one column is this label and the other 784 columns represents that 28 cross 28 pixels in the image. Now let's see how we can display this image. So for that, first we run a loop from 1 to 10, because let's say that we want to print first 10 images, or let's say we want to print just first 5 images, and then we just get the feature. So let's say that this data of 0 dot shape, it's data.ilog of shape. Yeah, you can see. So this first row, it has 785 columns, right? So let's just get the features or the X or the input. So for that, we just do data.ilog of I, and you can see that this first is this label. So we don't want the label, we just want the features. So we do like this, and let's see the shape of this feature, and let's break it. So it will be 784 basically. Yeah, you can see it is 784. Now we want to display this image using pyplot. So for that, we have to first convert this 784 shaped array into a 28 cross 28 array. So for that, let's do feature is equals to feature dot resize of 28 cross 28. So now its shape becomes 28 cross 28, and then we simply show this. So plt.im show of this feature, and this CMap is equals gray, and then finally plt.show to show the image. Okay, so the series object has no attribute as resize. So actually it's reshape. It's my bad. So reshape. Alright, so we are doing one mistake, and that is this one is a simple normal array. So this is a normal array, but we want to convert this into a numpy array so that we can use this reshape and everything. So for converting this normal array into an numpy array, we do feature is equals to np.array of feature. And let's see now. So you can see this first image is representing a 5. So it is 28 over here and 28 over here, and it is showing an image of 5. Now let's say I want to see the first 10 images. So yeah, this is how it looks. So first we have 5, then we have an image of 0, then 4, then 1, 9, 2, 1, 3, 1, 4, right? So this is how we can display these images. So we have the dataset. Now we want to extract the features, this X and the labels. So we want to separate them. So for that we have this data, which is a pandas data frame. So this is a pandas data frame, and from that we separate our X and we separate our Y. So for that we do the data dot drop of label, and axis is equals 1. So as you remember in our data, over here this is our pandas data frame, and you can see that there are 785 columns, and the name of this column, which represents the output, is label. So while extracting the features or the X, we don't want this label, so we are data dot drop, so we are dropping this column, and we do axis equals 1 because axis equals 1 denotes that we want to drop a column. So this one makes sense, right? And for getting the Y, we do data of label. So this Y or this output is nothing but just this column, right? So we do data of this label, which gets this one, 50419. And next, once we got this X and Y, we simply do train test split. So for that, we simply use our train test split module coming from scikit-learn, and we do a test size of 0.2, which means our training set will have 80% of the data and our test set will have just 20% of the data. And then we apply some standard scaling on our train and our test features so that they are all normalized from 0 to 1, because we know that neural networks, they work brilliant when the input and the values are normalized. So we do this on our train and our test features, these two. And once it has been done, we convert these features and labels to numpy arrays. So for that we do xtrain is equals xtrain.values. So like this xtrain, they are now pandas series, and for converting this panda series into numpy arrays, we just do dot values. So that makes this panda series into a numpy array. Makes sense? Alright. So let's do it now. So first is, let's extract the features and labels. So for that, x is nothing but data dot drop of our label, because that is the name of our column. So label, and access is equals 1, and we get the label which is data of label. Now let's see the x dot shape and the y dot shape. Yeah, so the x shape is 60,000 cross 784. So each of them have 784 columns, and then our label, it has a shape of 60,000 and it has no columns because it is just one single integer. Next, let's do the train test split. So xtrain, xtest, ytrain, and our ytest is equals to the train test split of our x, y, and we pass a test size of 0.2. Right, and let's see the shape of them. So xtrain dot shape, xtest dot shape, and our ytrain dot shape, and our ytest dot shape. So you can see that the xtrain, it has 48,000 rows cross 784 columns, and our xtest, it has just 12,000 rows. So together they make the 60,000 rows, and the same concept goes with our ytrain and ytest. And then let's apply the standard scaling so that the values are normalized, and we apply this standard scaling only on the features. So xtrain is equals to, like we are dividing it by 255, and xtest we do the same thing. Cool. And so this thing is done, and then we convert them to a numpy arrays. So let's see what they are actually. So type of this xtrain, so you can see that they are in pandas.core.frame.data frame. Now to convert this into numpy array, we simply do dot values. So xtrain is equals xtrain.values. Similarly, xtest is equals xtest.values. The same thing we do with ytrain and ytest. So ytrain is equals ytrain.values, and ytest is equals to ytest.values. And now if I do the type of this xtrain, you're going to see that it is a numpy array. Cool. So it's done. Next, let's see this dataset thing. So for that, we saw in the earlier lecture how datasets and data loaders, they work brilliantly for handling data in PyTorch. So for that, we first create a custom dataset class, which is inherited from this dataset coming from PyTorch. And we have three methods. So underscore init, underscore len, and underscore get item. And in this init, we are taking the features and labels, which are nothing but the x and y, and we are setting the self.x and self.y as torch.tensor. So here we are converting the numpy arrays into torch tensors, and it is a very crucial step because in neural network training we work with PyTorch tensors. We don't work with numpy arrays, right? So here we convert this into torch tensors, and the data type is float32. And very important thing is that in deep learning we convert our features or our x, like we keep them in floating values. So we make them their data type as float 32 or even float 64. So we make this a floating value, and for the labels or for this y, we make them the long, which is nothing but the integer value. Alright. And then we have this len function, which is returning the shape of 0, which is nothing but the you can say the number of data rows. So this represents nothing but the number of data rows or the number of entries or samples that we have. And then this underscore get item, which gets this index, and it returns the feature and the label present at that index. So this is our first step. Next, we create the dataset objects for our training and test data. So we use this custom dataset class and we create our dataset objects, wherein we pass our xtrain and our ytrain for this train dataset, and for this test dataset we pass the xtest and the ytest. And then we simply create the data loaders. So we create data loaders for both this training and test datasets. So train loader equals data loader of this train dataset. We're using a batch size of 32, and we're using a random sampler for shuffling this data in case of this train data loader, and we are pinning memory if our GPU is available, and that we do the same thing with the test loader. Alright, now let's see how it's done. So first let's create the dataset class or the custom dataset class. So I'm gonna name it the MNIST Dataset, and it's coming from this dataset, and das first method is init method, which takes this x, which is the features, and the y, which is the labels, and we make them as torch.tensor. So torch.tensor of this x, and as I told, we keep the data type of features in float, so it will be torch.float32, and the self.y is equals to torch.tensor of y, where the data type is long. And then we have a len function which returns the length or the number of data rows or entries present. So len takes a self and it returns a self.x of shape of 0. So this self.x, which is this one, is a torch tensor. So we can do this dot shape, and from that we are taking the 0th index, which represents the number of rows or the number of entries present. And lastly we have this get item function, which simply takes an index and it returns the feature and label present at that index. So return self.x of index and self.y of index. Next we create the dataset objects. So trained dataset is equals to, we named it as the MNIST dataset. So MNIST dataset, and it takes two things, x and y. So for this train dataset we pass, for x and y, we pass the x train and the y train, and for the test dataset the process is same, but here for this x and y we pass the x test and the y test. Brilliant. Now we can definitely run this len of this train dataset and the len of this test dataset. So you can see in our train dataset we have 48,000 entries, and in our test dataset we have 12,000 entries. And the final step is to create the data loaders for this train and testing. So train loader, something but this data loader of train dataset, and then we want to specify a batch size. So batch size is, we are preferring a batch size of 32, and then we are shuffling this data set, so shuffle of true, and we are pinning our memory if our GPU is available. So torch.coda.is available, right? And we do the same thing with the test loader, where we are passing the test data set and batch size is 32, and we are not shuffling this test data loader, because it generally doesn't matter if you are shuffling this test data set, because our model, it has nothing to do with this test data set. It is just being inferenced, or it is just being evaluated on it. It is not getting trained on it. So we can make its shuffle as false. And the same thing with pin memory. So let's see how one batch looks in this train loader. So for batch X, batch Y, in this train loader, let me see their shape. So print batch X dot shape, the batch of Y dot shape, and let me just break it. So you can see each batch in this train loader, it looks like this. So our this batch of X, or our batch features, it has a shape of 32 cross 784. Why 32? Because our batch size is 32. So in each batch we have 32 items or rows or entries, and the number of features or the columns is 784. And for this batch Y, its shape is only 32 because it has no columns, because it is just one single integer. So that is it for this section. Let's go to the modeling. So for the modeling, we first create a neural network class inheriting from this NN module. So this is our neural network class inheriting from this NN module, and in this init function we are taking this num of features, which is nothing but the 784, and then we are simply making this model. So self.model of nn.sequential. So sequential is used for stacking layers. So let's say that this is one layer. Using this sequential, we can like stack all these layers. So like it's like this. So each one of this is a layer, and we are stacking these layers one top of another using this sequential. So our first layer is having an input features of 784. So this is nothing but 784, and it is outputting 512 features. Then in the second layer we are taking 512 and outputting 256 neurons. Then over here we are inputting 256 because this has to be the same, and outputting 128. Then over this layer we are taking 128 and we are outputting 64. And then here we are taking 64 and outputting 32. And over here we are taking 32 and we are outputting 10. This 10 is the number of classes. Alright. So how it looks is that we have total of 1, 2, 3, 4, 5, 6. So we have 6 layers. So these are the 6 layers. So this layer, you can say this one, it is taking 784 features and outputting 512 features only. So you can say that these are all 784 features, and it is outputting 512 features. So you can see that we are downgrading. Then this layer, it is taking this 512 and it is outputting 256. So it takes this and it is outputting 256. And then this layer, it is taking 256 and outputting 128. And likewise we do this until we reach a point of number of flashes, which is 10 in our case. Alright, so it is basic deep learning stuff. And in the forward pass, we have our features, which is the batch size cross the number of features. So we saw that each batch is 32 cross 784. So that we have, and we are passing this to our model. And this model, this will go to our NN or our neural network, and it will make it, or it will reduce it into a shape of 32 cross 10. So you can see that we had 784 features as the input like this, and we are outputting to this 10 features. So this was the input, it came to this neural network, and this was how the output tensor is looking. And we are simply returning this output. Alright. Then we are defining some parameters. So this is our learning rate parameter, our number of epochs. So how many epochs we are training this neural network for. We define our model. We move it to the device. We define our loss function. In this case, we are using the cross entropy loss, as it is a multi-class classification because the number of classes is 10. And then we are defining an optimizer, which is this Adam optimizer. So here we pass the parameters and the learning rate. So let's go. So here we're defining the model. So class, let's say it's a MNIST neural network, and it is basically inheriting from the NN module. So NN.module, and in this init function we are taking two things. One is the number of features. Let me call it the n features. So n features and n classes. So this is 10 in our case. So first we have to call this init function of this NN module or of this parent module. So super.init. Yeah, and let's code this neural network. So self.nn is equals to nn.sequential, and I'm just simply pasting it because it's the same thing. So it will be number of n features over here. So it is 784 in our case. Yep. And this is how it works. And instead of this 10, I'm passing this n classes. Alright, and in this def forward method, we are taking this input as x, and we are calculating the output. So self.nn of x, and we're returning this output. Cool. Now let's create an instance of this model. So model is equals to, okay, actually let's not name it as NN because we have already this NN module, so it might have some problems. So self.model and self.model, and yeah. So now let's create a model. So model equals to this MNIST neural network. So we are creating an object of this class, and here we are passing two things. We have to pass two things: number of features and number of classes. So number of features is 784 in this case. So let's do xtrain dot shape of 1, which returns 784, and the number of classes, which is 10. And then we are moving this model to our device. And lastly, I want to print this model. So yeah, so here is how it looks. So this model looks like this. So we're taking this 784, like each of them is a layer, you can say. So it's taking 784, outputting 512 neurons, and this whole process goes till it becomes 10 neurons or 10 features, you can say. And let's define some important stuff for training. So learning rate is equals 3e minus 4, and number of epochs, let me say that it is I want to run the loop for 10 epochs, and let's create a function, a loss function. So it is nothing but nn dot cross entropy loss, and then we have an optimizer. So optimizer, and let's say that we want to use the Adam optimizer. So optim.adam, and first here we want to have to pass this parameters. So model dot parameters, and we have to pass the learning rate. So learning rate equals learning rate, and that is it for this section. Now let's go to this training loop. So in this training loop, we are running a loop for number of epoch times. We are making the model status as train status, and then we are initializing a variable as total epoch loss, which is initialized with 0. So its task is to accumulate the loss across all these batches. So inside each epoch, we are training for number of batches. So let's say that we have n number of batches. So in each epoch, we are training n number of batches. So we are training for n number of batches, and likewise we do that for number of epochs. So in each epoch, we are training our model for n times, like for this n number of batches, and that we do for this number of epochs. So this is the number of epoch times, and in each epoch we are training for n number of times. So total it is n times n. So we are training our model for these many times. So it's n cross n, where this n it is the number of where this n it is this number of epochs, and this n is the number of batches. Alright, so we are running a loop for getting this batch X and batch labels from this train loader. We are moving this batch features and label to this device. Then we are doing the forward pass. So y hat is equals to model of batch X. Then we are calculating the loss. So equals loss function of y hat and this y. Then we are resetting the gradients, calculating the, like we are computing the gradients, and then we are making the parameters update. And lastly, we are accumulating. So this is our total epoch loss. So we are updating this variable and we are adding to it the loss. So this is the loss from this particular batch. So the idea is in each epoch we are training for n number of times, okay? And while training, we are accumulating the batch loss. So at the end, let's say that this whole process is done. So now this total epoch loss, it contains the total loss accumulated across all the batches. So we use this to get our average epoch loss. So for getting that, we simply divide this total epoch loss by the len of train loader, which is nothing but the number of batches. So this is the number of batches n. So we are accumulating the entire loss across all the batches. Then we are dividing it by the number of batches we have. So then we get the average loss. And at the end we are outputting this loss. Cool. So let's actually code it. So here is our train. So for EP or for epoch in the range of n of epochs, first we have to toggle the status of our model to training. Then I want to initialize a variable of total epoch loss, which calculates the entire epoch loss. And then I want to run a loop. So for batch X and batch Y in train loader. And first we have to move this batch X and batch Y into the respective device. So batch X is equals to batch X dot to device. Same we do with this Y. And then we do the forward propagation. So y hat or the y pred is equals to this model. In this model, we are passing the batch of X. Then we calculate the loss. So loss is equals to loss function of this y hat and this batch Y. So it will be batch underscore small y. And then we zero out the gradients to like get rid of the gradient accumulation problem that we talked earlier. So optimizer.zeroGrad, and then we calculate the gradients of this loss with respect to all the parameters with this line, and then lastly we update our parameters. So optimizer.step, and finally we are accumulating this loss for this batch. So plus equals to loss.item, and that is it. And lastly, once we have this total epoch loss for all these batches accumulated, we are getting the average epoch loss. So average epoch loss equals to total epoch loss by the len of train loader. So let's see how many batches we have. So len of train loader and len of this test loader. So in our train loader we have 1500 batches, and in our test loader we have 375 batches. So in each epoch this loop is running. So in each epoch, inside each epoch we are running this loop for this many times, and likewise we have 10 epochs, so that becomes times 10. So in this entire process of this training neural network, we are simply making 15,000 parameters update, right? So that is how this calculation works. Now let's get back to coding. So once we have this epoch loss, average epoch loss, let's print it. So print f, and let's say the epoch of, it is the epoch plus 1, because this epoch, it is starting from 0, but I don't want to show it as 0. I want to show it that it is starting from 1. So that is why epoch plus 1, divide by the n of epochs. So like this is how we are displaying it actually. And then the loss is simply this average epoch loss dot to f. Now let me make this runtime as GPU, and let's see how it's working. Alright, so I just got converted to GPU, and let me start this training process. So yeah, so it has started. So you can see that at the first epoch our loss is 0.24, and in our second epoch it is 0.13. Our third epoch it is 0.09, and it is continuously reducing, right? For this fourth epoch it's 0.7, 0.5, and it's going on decreasing. Yeah, so that means our model is actually learning, and the training is actually happening. So the training has been done, and this is how it looks like. Now what also you can do is you can initialize a variable over here which is an array. So let's say that it is train losses, and at the end you can just append it. So you can just append your loss into this train loss, and at the end you can also like plot this graph, so that you get a matplotlib graph where you are showing your loss curve. So you are showing that how your loss is actually decreasing across your number of epochs. So you can also do that, and I'm leaving it up to you because it is very simple. So yep, so that is it for this section. And lastly we have this evaluation loop. So for this what we do is we get the total number of levels, which is the length of this test dataset, which is in our case 12,000, and we initialize another variable as correct predictions, which is initialized by 0, and then we make the model status as eval. So earlier it was train, but now we are making its status as eval, and then we are disabling the gradient because training is done. Now we are doing inference. So for doing inference or evaluation, we don't want any gradient tracking, so we are disabling, and we run this loop. So for batch X and batch label across this test loader, we are converting our batch X and batch label into device. We are doing the forward pass, and then we are getting the predicted label. So it is torch.argmax of this y hat across the dimension 1. So this batch features is a shape of 32 cross 784. So you pass this to your neural network, this one, and you get your y hat or your y prets, which is of shape 32 cross number of classes, which is 10. And once you got it, you apply that torch.argmax along this dimension 1. So along this dimension 1, this one, which is the number of classes, you apply the torch.argmax so that you get this, like this class, which has the highest probability value. So this means that our neural network is basically, it is returning a probability for all these 10 classes. So it has 0 to 9. So our neural network is giving a probability for each of this class. And with this argmax, you are saying is that return me the class, or return me this digit from 0 to 9, or you can say that return me the class which has the highest probability. So whatever the neural network thinks that it has the highest probability, you are just getting that value. So its shape will be again 32, and batch labels was already 32. So you are comparing it. So here you are comparing it. So predicted labels is equals to batch labels. So it is again, you can say it is an array of 32 items containing only boolean values like true or false, or you can say that 0 or 1, and then you do dot sum so that you are actually getting the number of corrected predictions. Because let's say that this 32 items, we have let's say 22 zeros and 12 1. Then if we are doing this sum, we are getting only 12, right? So that means in this 32 items, we have only made 12 correct predictions. So that is how we are getting the number of correct predictions over here. And then we are accumulating it. So correct predictions was initialized as 0 over here. So we are accumulating it so that we are accumulating across all the batches. So this, we are accumulating the number of correct predictions across all the batches. And lastly, we are calculating this accuracy by dividing this correct predictions by the number of total labels, like this one. And we are getting this accuracy. And obviously this will be something like 0.50 or like 0.75 or like anything. So for making that into a percentage, you are multiplying that by 100. Simple concept. So let's go. So this is the evaluation. Yeah, so first we have the total breadths. We have the length of this test data set, which is obviously going to be 12. So 12,000, sorry. Yeah. And let's say that we want this correct predictions as 0. Now let's run the loop. So first we have to set the model status as eval, and then we have to first disable the gradient tracking, because we don't want to calculate any gradients, because here we are only doing inference. So with torch.nograd, and then we have to run a loop just like this one. So for batch X, batch Y in this test loader, then we have to convert them into the device. Now let's do the forward pass. So y pred equals to model of batch X, and then once we got it, let's accumulate this. So let's make it the total correct predictions, and let me name it as the batch correct predictions. Yeah, is equals to, so before that this was our ypred, which is batch size, which is 32 cross our number of classes, which is 10. So from here we have to first get the label which has the highest probability. So let me say that it is the predicted label as simply torch.argmax of this ypred and dimension equals 1. So now the shape is 32. So this batch y is also 32. So in this batch correct predictions, we are seeing that in this batch how many correct predictions are there. So is equals to batch y is equals to this predicted label, and then dot sum will simply give us the number of correct predictions that we have for this batch, and then we do dot item because it is a tensor. So for getting the value we do dot item, and that will, I guess, return me the number of correct predictions for this batch. And then using this total correct predictions we are accumulating the value. So yeah, so let's see how many total predictions we have. So it is obviously 12,000. Let's see how many correct predictions are there. So it is 11,685. So now let's get the accuracy. So it is this one divided by total predictions, and I want to make it a percentage. So this step is optional, but yeah, times 100.2f, and you can see that we are getting a percentage of 97.38. So this means that our neural network, which we just trained it on any unseen or any new dataset, it is getting 97 predictions right out of 100 predictions. So like, it is definitely a very good model, but obviously this can be improved by using techniques like batch normalization, dropouts, regularization, weight decay, everything. So we are going to see that in the upcoming lecture, but for now we are getting an accuracy of 97.38%, which is actually very good. So like, that is this for this lecture, and I hope that you all gained a lot of knowledge and understanding of how it all works. So that is it, and in the next lecture we are actually going to learn what is underfitting, overfitting, and we are going to see what are bias and variance, and we are going to see a lot of methods like batch normalization, dropouts, regularization, weight decay, which are used to reduce this overfitting and improve this model performance. So we are going to see that in the upcoming lectures. So yeah, that's it, and I'll see you in the next one.